Mark Baumgartner is a senior scientist at Woods Hole Oceanographic Institution. Back in 2011, he and Sarah Mussolini published a paper on how to use computer science to classify whales from sound recordings. This episode is about an evolution of that software by Atle Borsholm of NV5 Geospatial. I want you to listen to this sound recording and classify the whale making the calls in it. In my comments at the end of this episode, I'll tell you what whale that was. It was an easy one to process. The recording was just 7 seconds long, and a whale sound was present immediately. Consider if I instead gave you another one lasting a day, and most of it was just ocean noise. This leads to the challenge discussed in today's episode. Imagine I have 100 microphones under the ocean. These are called hydrophones. These hydrophones record for 24 days. The scientists managing them will say they now have 2,400 days of data to process. Well, that is nowhere near how big of a challenge this episode is about. The National Oceanic and Atmospheric Administration had 217,197 days of hydrophone recordings going back 20 years. Whilst Mark's software was available, it needed to be made more efficient to process all this data. It was worth the effort. It turned out that only 24,000 or 11% of those days involved a whale being detected. All of it is shown in NOAA's passive acoustic cetacean map. Atlas starts by discussing another web application, Mark's Robots for Whales website, in our episode today. My name's Wilfred Waters. Thank you for listening to Geospatial FM. Atle Borsholm, data scientist at NV5 Geospatial. It's a privilege to have you on Geospatial FM.
Great to be here. It's very current, the information on this website. Like you can see here, a species detected in the last 3 days. Sand. So this one actually allows you to sort of dig in. It doesn't have that many recording platforms right here. Like the other website we will look at has more historical data, but this is very current. So it's sort of, you can go in and get very up-to-date information here. You can sort of see what the detections were. You can go into a specific active device, and it'll have more information about that. For example, this one looks like they might have, this one might be one that's been towed, and you can sort of see here day by day on this mission when they detected particular whale types. And this has lots of information here on this website, but this is very updated very quickly, like you saw. And
was that a hydrophone there, that yellow thing, or is that a drone?
Yeah, this is one of these. They call them gliders. This is very fascinating technology, I think. So basically, you can deploy these gliders now. You can deploy these. They contain a hydrophone, and then they would have a means of communicating with satellite communication when it's at the surface. And then it can sort of be programmed to go to dive. Yeah, this is a slocum glider, so it can be programmed to dive to a certain depth, and it's using sort of oil hydraulics, like moving something from a higher density chamber to a lower density chamber to make it go up or down at different depths. And then some of these also have the ability to sort of move these little fins so that while it's sinking or going down or up, they can sort of steer the roll and pitch so that they can actually steer them to specific locations. And program it.
It's great to have, it's great to be stepped through some of the mechanics of devices made by companies in the hydrographic surveying part of the Geo 500. And that's another reason I'm excited to have you on, Atla, because you're talking about the use of these devices. And there's some really cool names for some of these companies like Coda Octopus and Kraken Robotics.
Absolutely. No, I found these are very fascinating. And then, you know, they collect a lot of data too now in a short amount of time. Like the older collection platforms might have 20 kilohertz or whatever recording, but typically now they would record up to 120 to 150 kilohertz. So that's a lot of samples per second that it's collecting. so after a few hours, you end up with a lot more data. But obviously, we can also handle more data now that we have a better storage and communication.
But then my mind is immediately on how that data is handled, and is it all stored on the device and then you retrieve it when you bring it back to the boat, or is it, you know, sent via a fiber optic cable if it's towed back to the boat in real time? I mean, I don't want to sort of derail the conversation, but that's where my mind's going.
No, that's interesting. They do have the towed what they call towed arrays where they are connected, but like these gliders can be completely just dumped into the water. They float up to the surface. They can communicate with like Iridium satellite or Starlink or whatever they're set up to, and somebody can program them to go on a 5-hour dive, collect data, then come back up to the surface.
Oh, so this is an autonomous
and then
vehicle.
It could actually, yeah,
It's not towed.
It could then, yeah, this one is not towed, but there are towed variations too that they use. So there's all kinds of.
Okay, so
varieties.
You mentioned Iridium and Starlink, but we should also mention Globalstar. Because they were recently purchased by Amazon this week. Okay, all right. Sorry, I'm trying to keep up with show that I do maintain this Geo 500 index with this company. Okay, yeah, cool. All right. Did you also mention there's the passive acoustic cetacean map, or at least some other?
Yes, that was the other website that I wanted to show. That has. I was looking at it recently. It has more historical data on it, but both of these websites, and this is the website right now. I hope you can see it.
Yep.
But both of these websites are using this. If you look in what's up on the screen right now, it says detection methods, LFDCS, and that was sort of the code in the background that I worked on in this project. So both this one and the previous website would use that. They also use some other software for some of the processing. So some of these dots on the map here might have a different detection method as well.
So what does LFDCS mean?
So it's low frequency detection and classification system. I think it's that's I'm pretty sure that's right.
Okay.
So it's just yeah. And by classification here they mean classifying the species of whale and the type of call, because each whale could have like a echolocation clicks or other calls that they make for a different purpose. So they classify it as, oh, this was a fin whale or a sei whale, and it was this type of click. So it's pretty specific.
Amazing. And so you came up with an algorithm here, or how did you go about creating LFDCS?
Yeah. So here, sorry. Yeah, so here you can see here there's the here's the name Baumgartner, which also was mentioned on the other website, and he actually was very involved in developing this algorithm originally using our our software, but he's a whale researcher and he was involved in that. The main work that I did was to modernize that and modernize that initial code that he had written, and also update it so that they could process on a much larger scale, because the original code that he wrote was more quote unquote research grade. So it was sort of, you had to have it could only run on some Macintosh systems and so forth. So I optimized the code and made it run so that they could run large amounts of data in a short amount of time. So which helps them with this quick reporting after you get a large amount of data as well. But certainly, I wouldn't want to take all the credit for coming up with the algorithm myself, but I know I have familiarity with how it works.
All right, so step us through the panels on the left, what you've pulled up at the bottom, and the legend on the right. Just help us understand what the components are of this app and what these dots mean, what an expert using it, or what kind of insights a user might try to derive.
Yeah. So this filter, or we call them filters here on the left-hand side, allows you to narrow down your search for what you're interested in looking for. So this is sort of a consolidation of data, and you can see that this isn't as current as the other one, but it has multiple years. It goes all the way back to 2005 when they started collecting data, and they've sort of posted everything here so that you can consolidate and look for patterns and so forth. So to go to these elements here on the left, you can limit, for example, the season. Say I only want to look at the late summer or something. I could say August to September. Now my dots immediately update so that I'm only getting that time frame. You can limit the years as well. You can also limit by so what, just to do the color coding here, is that on these, there's different types of missions. Some of these could be underwater for 30 days or longer, and some of them they just tow it and it's a shorter period of time. For example, this dot here represents a period. You can see monitoring period is pretty long, so it's several months, and then it's just when you click on it, you can then see the blue dots, meaning days when they didn't detect any whale sounds. So this sort of brings up the whole thing about finding these whale sounds at a particular time.
You're trying to find a fish in a haystack.
Yes, a fish in a haystack, exactly. Because you can imagine how many samples that you have to look through before you got to this one.
So is that saying that that poor little sensor on that mission spent, what, a month at sea and only on one day detected a whale?
Yeah, and this is a little bit simplified. It could be more because it's just saying that there was detections only on this day, but you would have to dig into it more to see exactly when in the day and if there was more, and usually it could be multiple times. But yeah, it's basically saying that there was a lot of days when there was nothing nothing detected here in this particular case.
Okay, so I guess this to me is maybe a segue into the agenda item of data abundance. Is it that the problem is there's a huge amount of noise and you need some way of actually finding signal?
Yeah, exactly. Here you can see there was a lot higher number of detections because I clicked on one of the bigger dots, meaning that there was more detections. But you're right. The data abundance is the real challenge in this case for the algorithm, is that there's just so much data to look through to find these pretty rare events in the grand scheme.
So if you've zoomed in there, that's nice. So we've got the gray tracks. Is that where each of these little underwater UAVs has sailed, if you like, or motored?
Yeah, exactly. So these are glider tracks. Well, yeah, most of these are glider tracks. They could be towed, but if you click on it, you can see that, for example, this one says wave glider. So it tells you, and then the recording device Demon, which you can look that up. That's a type of hydrophone, I guess. But
Okay.
yeah, those are paths that fit the search criteria here.
Okay, and the
you can
colors,
also you can also filter it over here, so that I could look for only gliders if I was only interested in those, for example. It took away the rest of it. So that was a wave glider.
Okay,
this is
that's
an
really
electric glider. Yeah.
Cool. Okay, so these are the different types of recording platforms. So were there 4 types of recording platforms on this web app?
Yeah.
Yeah.
Yeah, exactly. So yeah, this is this is telling us well, mostly this is useful for looking at historical data.
Right, and it's really showing how I mean those tracks there are it's gliding all over the place.
Yeah. This the scale here is, you can see now, since this is actually only the North Atlantic right whale I'm looking at here, so that's why there's only gliders over here. If you did blue whale, you would get something over in the Pacific, I think, although I don't know if they, yeah. So then you get stuff over here, right?
Wow. Okay, so there's a
but
huge
they're
amount of
pretty far, pretty far. Yeah, huge amount of data over a long period. This is 20 years worth of data.
What you've put in front of us is a web app with data about whales, not whale sightings, but whale hearings. Going back 20 years, both sides of the US, a couple of oceans. Would be interesting to hear any comments in this context about the data science approaches you employed.
It's a good lead into the data science part of this. It's been sort of a theme of what I've been working on for the last 20 years is to extract information from data that's more raw and closer to the sensor. But this was really the first time I got to work with these hydrophones, and it's very, it's a very interesting experience. There's sort of 2 ways you can think of attacking this problem of finding the sounds in the large amount of data. There's kind of the more traditional programming approach, which is basically you would create a set of rules that say, if based on an amplitude or frequency of a sound, you say that, okay, that might be an echolocation click that a whale might make, and if we hear 10 of those in 20 seconds, then we say that it's this species. But then other calls are totally different than an echolocation click, sound very different, and you would have to program specific rules for that. So that's sort of the traditional way of programming rules-based detection, which I think, at the beginning, back in 2005, that was probably pretty prevalent. But now the more common way of doing this is what we call supervised learning. So the example that I'm more familiar with this, and you probably also too, is this is kind of like, they use in face recognition or object detection, like military applications might look for airplanes or ships or tanks or something in images. So, and the way that the supervised learning, I'm sure you're pretty familiar with that concept. It's basically saying that instead of coding a set of rules, you just give you find a lot of examples of what you want to find, but you have to have a lot of examples. So the downside is you have to have a lot of examples of what you're looking for. The upside is that you don't have to code any specific rules, because sort of the model that you use, once it's given these examples, the model is sort of optimized to give you the correct answer based on these known examples. Of course, the downside to that, yeah, go ahead.
Yeah. So does that mean there's a strong partnership then with researchers who have gotten out and chased the whales, as it were, on some sort of a boat? I have this, image in my mind of, some hardy seafaring voyage, ice crystal encrusted beard. There's the whale. I don't know. Is it that
exactly? Yeah.
So you depend on them for some sort of a data set? Oh, I'm imagining huge amounts of MP3 files or something with the file name. This is this whale doing this, and I'm oversimplifying dramatically there.
Yeah, that's kind of how I think of it, is that these whale experts, they can listen to that, and they've been out in the field and they know what the different whales sound like. And of course there's some variation, but then they would listen to a bunch of recordings, and then they would categorize and say that these examples all fit into that category, this species and this call, and then these other MP3 samples fit into the other category. I mean, that's basically how you come up with that, and to do it with the neural nets, you sort of, the more examples you have, the better, right? So that's but the difficulty there is that you would have an expert have to say what each of those examples were, right, to make sure that you're getting the right call. So we were using some of these supervised learning models that are a little bit simpler, where it's not, there's a range of methods, that some that require fewer examples, but still you would need a fair amount of examples even for the methodology we used here. So yeah, you absolutely need the experts telling you which ones.
So yes, I mean, I've done a bit in remote sensing, honestly, mainly around mosaicing Worldview 2 imagery, auto-rectifying and mosaicing Worldview 2 imagery over the Bergen oil field in Kuwait, which is vaguely topical given the conflict with Iran and the rest of the world at the moment. Maybe I should go and check out the latest satellite imagery. I don't think they have attacked that oil field. Anyway, so I'm wondering if the same algorithms used for supervised learning, for example, with remote sensing or data or imagery, essentially, these large raster files, can the same algorithms be used for big audio data?
Yes, exactly. You can use almost all of these specific algorithms, such as, like, there's you can mention a random forest is one that's being used. Support vector machine is another early one, and then neural networks, and there's others too. and you can apply all of these to the same. So once you have that data, you can actually compare all of these algorithms to each other, and it absolutely can be applied to sound data as well as satellite imagery.
Yeah,
So,
that's really interesting because maybe it opens the eyes of your average remote sensing analyst who might think they're only useful for what you can see, but you're saying they're general purpose algorithms. That's interesting to hear.
Yeah. The only slight difference there is that in imagery we also use these convolutional neural networks where you do a spatial convolution, and obviously that depends on 2 dimensions, the spatial part. But otherwise, slight modifications in those neural networks, you can apply those to the sound as well. So it doesn't matter.
So when you were saying echolocation clicks, you were making these whales sound like bats. So do all whales kind of have these 2 modes where they're using sound to try and see how far they are away from some sort of hard object, and also they have another set of sounds to talk with each other? Is that the case?
Yeah, that's that's what I learned here, is that there's not all whale species use echolocation, I think, but some of them do, or many of them do. And again, I'm not a whale expert, but that's what I see from from the experts, at least.
So was there one kind of sound emittance that was more common than the other one? I mean, was it easier to make an identification using the echolocation clicks or the general purpose talking sounds? Just interested in some detail.
Yeah. I mean, the nice thing about the algorithm is that with the supervised learning, you sort of don't really care what it sounds like as long as you give it enough examples. But obviously, you could typically get a better accuracy if it's a more distinct sound, because it's statistically closer to or further away from. If it's statistically more separate from the other sounds, then
the background noise
code is going to have a better. It's going to have a easier time really getting it right. If it's
so that's a key step
distinct,
then, is to find something that's distinct in some way, regardless of whether it's a submarine propeller or from a whale. At least there's something that's different from what generally goes on around the hydrophone. It sounds like that's the first step.
Yes, exactly. And sometimes it can be kind of faint because they're very far away. So they can be, the signals can. The hydrophones also are getting better and better, like the minimum noise floor is sort of, it can detect to a better, less impacted by the noise, I guess. There's things like that. They also have noise reduction algorithms, and we used some pre-processing with just noise, some Fourier transforms and noise reduction algorithms as well that you can apply.
Were there any particular challenges, anything unique to do with big audio data?
There are some good formats for compressing sound with minimal losses. So I actually worked with them on that as well to sort of support this, to add support for these newer compression algorithms. So that's kind of nice, because once we sort of uncompress everything to analyze it, but when you want to do long-term storage, it makes it cheaper on your AWS or whatever you're paying for, that's or Google or something. It's cheaper if you have it compressed. So that's a good thing. But yeah, no, the biggest one of the challenges here is that my background is coming from sort of a lot of imagery and remote sensing data, that kind of display, and not sound. So we had to make sure that they had convenient ways of being able to click and listen to something, to listen to some of these sounds.
You've brought up cloud computing too, and that's a hot topic in geospatial as well. So did you use AWS, and did it just like all the big cloud computing platforms seem to come out of the box with being able to do some sort of spatial queries natively? Do any of these cloud computing platforms also come with some out of the box capacity to process audio data in some special useful way?
Yeah, no, it wasn't really. We did use AWS computing, but there wasn't anything that special because we had sort of implemented everything self-contained so that it would run from the container, so they could run it on their premises or on the cloud, just to make it more flexible. But no, I don't think there was anything specific. I mean, there's obviously the GPU capabilities that you can have on some of the cloud instances, which can be a very good thing. We use those sometimes, but again, the fact that you can run so many processes in parallel sometimes make it easier and cheaper to run more instances in parallel. If you have 1,000 sound files, you can run 1,000 cheap CPU based images instead of paying for the more expensive GPU compute.
Always nice to hear. I'm always keen to pop the GPU bubble, so nice to hear some solid criticism there. Okay, so then in summary, you put in front of us a couple of web apps showing locations of whale hearings rather than sightings, as I was saying before.
Yes.
And one of them was, it seemed like almost by the hour or by the day, these were the detections. And then the second one you showed us was going as more of a historical study going back 20 years. And you gave us examples of how you could slice and dice the data and see by the time of the year the whale sightings and the kinds of sensors that were detecting them. Then we spoke about some of the algorithms used, the way the data was stored, and the challenge of detecting amongst the noise what a likely actual sound emittance of a whale might be. So I guess now that you've sort of set the scene for us, what was the meaning of these analyses for a downstream user? What was some meaningful insight they got and that they didn't have before you did what you did?
Yeah, so I think that I mean the customer, they were very. Noah was very happy with the outcome of this. The fact that they actually had a fairly large amount of historical data laying around that they just hadn't had a chance to process. So they're getting a much more complete picture of what's going on with the trends over time, I think, by filling in the gaps of what hadn't been processed, from various missions. So that part I think is good, and then of course this more this ability to get a more quick turnaround time on getting an answer, I think, is a useful outcome to them, right? That they can very quickly turn around and act based on new information. But
do you know how long they had to wait before you modernized the script?
Yeah, something where that something. I mean, it was on the order of. It could be in the order of. I mean, 50 to 100 times faster, I think.
Okay.
But it was also more that they could sort of run it more without human interaction. So it's more like giving them the ability to more easily run a large a large set of data without having to click on or do every single file and then wait a long time and so forth.
Yeah.
So yeah, they can get a lot more throughput that way.
Yeah. Okay.
Yeah, and scalability. So
Yeah.
but no, I haven't heard anything else specific other than they're happy about the speed improvement on specifically. And the data format too, the compression was important to them to support.
Yeah. I'm wondering if you could briefly bring the app back up, because I noticed that
Sure.
there was more frequency of whale detections some years than others. If you zoom out, oh, okay, you've got the bar chart on the left there. So there's, two peaks in the middle one. What are those two peaks?
Here?
Yeah, and then there's another one a couple of years later. Are those years or months?
These are not, well, 2015, 16, 17, 18, 19. Yeah, these are years.
Okay.
So 2016 actually had more detections. Although I could take away, I could just show the detected. So
okay, there we go.
So that you can sort of really see that.
So and those are which kind of whales? The
well,
blue
this
whales.
one is the blue whale.
And those are the biggest ones, right? Those are the ones that are the size of a school bus kind of thing.
Yeah, blue whale is also the most rare, I think.
Right.
Well, actually, I'm not sure about that, because the North Atlantic right whale, I thought they said was endangered now. So that one also. Let me see here if I show the detections. Yeah, so you can see that there's more detections maybe in the winter than in the summer, which is interesting, but also by year here.
Okay,
It's
so for those ones
seemed
by
like it's
year,
going down.
yeah, it does look like there's a downward trend in the past half decade, but still over that whole over the whole data series, so the past 20 years, I mean, it looks relatively constant compared to the blue whale, where there were two peaks and there was a few years where there were no detections at all. So was that something that they weren't aware of before you did this analysis?
I'm not 100% sure about this. You see this gap here. One thing is that overall numbers are fairly low for the blue whales. And I guess another thing to consider here is that, like, if we go back to the right whale, sorry, I keep going back and forth here, but if we go back to the right whale, one thing to consider too is that the microphone technology has gotten better, but yet we're not seeing like a big upswing in the number of detections, even though you would assume that the microphones are better able to detect. The newer equipment should be able to detect more, but you're not necessarily seeing an uptake.
My eyeballs line of best fit is putting a vague upward inclination on that middle chart there, but not for the blue whale one. So yeah, these sorts of things are very interesting.
Yeah, it is. It is an interesting, and yeah, this is. I guess you can put the link up for this.
Could you go down to another whale just out of interest? Just any other one, like a sperm whale or something?
I did humpback whale.
Yeah. Okay. Could you just show the detections? So there we go. Now my eyeball is putting quite a distinct line of best fit going up. Yeah.
You see a little bit of an upswing here.
Okay.
Yeah.
And again,
so it is interesting.
Yeah, and the summer months it's down. So is that because they migrate to cooler water in the southern hemisphere?
Yeah, it might be. It might be that they migrate. Yeah,
because we get humpback whales in Australia. I know
exactly.
for example, and you can see Australia in the southern hemisphere there, maybe not too far away from the perspective of a humpback whale. It's just a casual trip across the Pacific Ocean. And then, because I know
it would go here.
Yeah,
Yeah.
so we need a global version of this map. We need all the hydrophones, and we need to run your algorithm on all of them, and we can see them migrating. So there's fascinating applications here, or ways that you could develop this, but to basically turn it into an AIS tracker for whales. So you can, I mean, similar to how you can have animations of ship traffic. And I guess there are plenty of transponders that have been glued to the backs of whales, but that's a whole nother conversation, I suppose. So, yeah.
Yeah, very interesting. Maybe have something like face recognition, except for whale call recognition, so you can distinguish individuals. That might be the next step. I'm up for that.
Awesome.
Let's do that and set it a date in 5 years.
Okay. All right. Well, yeah. Once again, yeah, amazing, Atle Bolson, data scientist at NV5 Geospatial. Amazing to have this opportunity to dip in to what NV5 does around what sounds like the everyday processing LiDAR data, doing topographic surveys, all of this. You also look after the whales. So yeah, really great to have that insight.
Mm-hmm. Thank you so much.
The only issue left to cover is that we're in the age of artificial general intelligence, and I foreshadowed that by putting on the screen during the introduction the classification of that seconds-long whale recording by Claude, ChatGPT, and Gemini. I also said I'd tell you what the whale was. So it was a humpback whale, and Gemini was the only one that got it right. So how can we think about what Atle put in front of us, and also, Mark Baumgartner's work from back in 2011? What does all of this mean in the context of having Claude, ChatGPT, and Gemini? Well, I'm sure that the leadership at NV5 Geospatial are thinking carefully about if they can rely on this kind of software development work, this kind of consulting work in the future. These three systems and others are developing at an extremely rapid pace. It's, in the realm of weeks, that we can expect an improvement in these systems' ability to classify these whale sounds. Maybe in a month from now, Claude and ChatGPT will also be able to get the classification correct. So all I can say is, I think we're all in this boat together. We're all wondering, what will happen and what revenue will go away, and hopefully what revenue might replace it. So I guess really where this episode leaves me is thinking about how we can either leverage these existing three platforms and others to replace, I'm sorry to say this, but to do what Atle was employed to do, and NV5 Geospatial more broadly. But also, these companies are probably, I expect, pouring money into investing in their own, for example, whale GPT. I think that's a nice positive way to put things. Let's think about how we can develop a artificial general intelligence system that allows us to not only listen to whales, but even in the end to talk to them.